So you guys need to know everything that I put on the board, which is this whole first section right here. You need to know what it's called, what its name is, what its structure is, whether you're losing or gaining hydrogens. So this is what I was saying where I'm still playing with the structure. There's like the acetyl-CoA one, which is probably to the acetylcholine, to the choline one, which is worth like 5 or 6 points. There's the intrinsic factor B12 one, which is worth 5 or 6 points. And this type of drawing that I need you guys to know is worth 5 or 6 points. So that's why I'm toying with giving you a choice of like 3 or 4 little ones and then 2 or 3 big ones versus 3 or 4 big ones. So we'll see how that, you'll know by Monday, because I have to know by Monday. So, all right, so even though the light was on, it says this. All right, so this is ascorbic acid. So citric acid is not vitamin C. Ascorbic acid is vitamin C. And I'm pointing that out because it's a question on your exercise, so don't get fooled, okay? All right, so we've got multiple forms. We've got ascorbic acid, which is protonated, meaning every O is saturated with an H. We've got ascorbate, which is an ionized form, which means one hydrogen is missing an H, right? You turned it into an ion, it has a negative charge. You've got the ascorbyl radical, which means you've removed both H's, but you have a resonance structure whereby that thing is rotating around in between all these different bonds. And then you have dehydroascorbic acid, which means all possible H's are off, right? It's the most oxidized form because you remove the most electrons and also by that the protons. This one at physiologic pH is very unstable. This will fall apart within minutes. So at physiologic pH, we spend most of our time going back and forth between these three. That is because this allows us to absorb those free radicals, those extra electrons that can hop around and do damage to other molecules. Again, no determinism, not really because, but it turns out that the fact that ascorbic acid is capable of becoming ascorbate and then the ascorbyl radical, it can absorb this and then go in either direction, which allows us to, then if you absorb this free radical, right, then you can lose it and go in the other direction, and then you can fall apart. So it'll be easier if we draw it. Now I'm going to point out one more thing. Most animals, and I wrote it on the board. So what's this? This is glucose, right? If you look at the structure of ascorbic acid, it's based on glucose. It should look familiar, even though it's different. Like it should look familiar. Like when you draw, if you're writing it out and drawing it, you're going, this seems like a similar number of carbons. It seems like a similar number of oxygens. It seems like if you drew glucose in a ring structure, you would have that extra little piece sticking off where the 6th carbon is coming from. So we cannot. We lack the enzyme that allows us to go from here to here, which is guanolactone oxidase. We can't go from here to here. A couple other animals can't either. Primates, a couple selected other mammals. Every other species can. So we have to go get vitamin C or ascorbic acid. So I'm going to go now. We're going to look at it on the board and then we'll be done. Okay, so as I said up here, most animals can make ascorbic acid from glucose. We can't because we lack this enzyme. I'm not going to ask you to name the enzyme, but you should know why we can't, because we're missing an enzyme that allows us to go forward. All right, so here's our ascorbic acid, and I wrote down here, this is reduced versus oxidized. Loss of electron equals oxidation, right? Gain of electron is reduction. So you can follow that through in the arrows. First, you have to lose the proton, right? So this is completely protonated, meaning it's got H's on all of the O's. The next step is you lose the proton, right? And this is a minus going in this direction and a plus, because you can go backward and put the proton back on if you happen to have extra proton. This minus can come off here or here. They draw it mostly coming off here because there's something slightly different about this structure versus this structure. It is much more likely to come off over here than it is to come off over there. Doesn't mean it has to happen first that way, it just means probabilistically it's more likely to come off of here first. Okay, so now we've got we lose another electron, or another proton and an electron. So now we have an ascorbyl radical, and this is a copy of the thing in the book where it has the dot and the minus. That means it's an extra electron. Now, as we talked about before, oxygen is kind of flexible. It's willing, it prefers to have its valence state filled, but it can take 1 or 2 extra electrons. You can get, O2 minus or an O2 2 minus, and it can sustain that structure for a small period of time. So this structure, this is sorbal radical structure, all right. Look at all these O's right next to each other. They can share the load of this electron. It can move back and forth, and each O only has to hold that extra negative for a small period of time. So that gives it the ability to stay relatively stable, because if you have an O2 2 minus or an O2 minus, and you're just looking at those 2 O's stuck together with the extra electron, it wants to go dump that electron. That's why it's a reactive oxygen species, because it will go find some place to put that electron, some other molecule, and it will destroy it. This has so many oxygens right here, and all these little dots, and you'll see them better in the book. I wish I had, like I said, green so you can see. Right? This is sharing the load of that extra electron. That gives it the ability to be relatively stable, because this electron, well, you consider it in math, it's taking, 1/5 of the load. Actually, it's just staying here for 1/5 of the time. It just floats around in space. So it gets attracted to this, and then it gets attracted to that, and then it gets attracted to that, so that these bonds don't have time to become destabilized, because the electron has moved fast enough. So then you can lose that electron that's floating around, and then you can end up here in dihydrosorbic acid. What that means is, look at these bonds, right? These are both going from a single, like over there with 2 alcohols on. Now we've got the equivalent, we're in a ring, but the equivalent of 2 ketone bonds. So they're maximally oxidized. And like I said, very unstable at physiologic pH. This will fall apart into a non-ring structure and then can get broken down. So once you get over here, right, once you've lost that other electron, you can break it down. You can run it in the other direction too. So just to recap, we need to know everything that I put on the board right now except for the specific name of the enzyme. This is another good, like, 5-point-ish question to throw up there. You do need to be able to recognize ascorbic acid as well, right? Like, it's fair game for just the structural recognition, but you need to be able to draw all this. And we're also going to draw how vitamin E works. So you're going to have to answer at least 1 of 2 reduction oxidation structure questions. Okay, I'll take a picture of this.
This is exactly what's in the book.
Yes, this is exactly what's in the book. I just put it up so that I could talk about it better than me like pointing at the book.